Hello, Scotty. John here. Wanted to talk to you a little bit about some of the questions we discussed today. So we'll be talking about the second derivative and inflection and just kind of how a lot of that works. So here I've drawn a curve that very clearly exemplifies the idea of inflection. Um, so if you look at right here on this side of the curve, you'll see that it is concave upward, and so that's the term we use to describe when something would, the analogy they use all the time is something that would catch water. So if water were to fall down here, it would definitely catch water, whereas if water fell somewhere right here, it would just fall out and it wouldn't catch anything. And so there is a point somewhere right around here or so um, where it switches from being something that is concave upwards to something that is concave downwards. And so that is where we can get the idea of the second derivative and inflection. And so this is the point of inflection. This is the point where it switches from being something that's concave upward to suddenly now it's something that's concave downward. You'll notice that it is still increasing at this point, so the slope is still positive. It's only right around here that the slope starts to become negative. But the slope can still be positive even after the point of inflection, but it'll be positive at a decreasing rate. Whereas over here, the slope will be positive after right here. So here the slope is positive, but at an increasing rate. So it keeps getting greater and greater, faster and faster. Here, the slope is still positive, but it starts slowing down, and the slope is getting less positive until the slope becomes 0, and then here the slope finally becomes negative, and it will go down there. Anyway, so we will talk a little bit about points of inflection. That's kind of just an idea, so I wanted to give you a picture that kind of shows inflection very clearly. Let's get to a more specific example. So here I've drawn some graphs that I thought might be relevant. So the first graph shows f of x equals x to the fourth minus 2x cubed. And so that's this graph up here. So what you have is, your main function or your primary driving function is going to be x to the fourth. So as you go off, that's going to make it basically like a parabola, but then as you get in here close to 0, this minus 2x cubed part of the function is going to have a greater effect. And so that's where you see this part of the graph showing up. That comes from the negative, this funny like S shape comes from the where the negative 2x cubed is more prominent, but the going off any other direction, that comes from the biggest part, the x to the fourth. But so what the question asks us to do is it asks us to find the points of inflection along here. And so it might be kind of hard to see, but there is a point right around in here where it's going to switch from, you see that it is concave. It's definitely concave up here, and then it's hard to tell what it would be over here, what it would be over here, all that stuff. So first thing we do is we take the first derivative. So you see f prime of x equals 4x cubed minus 6x squared. And so I've graphed that one down here. So you've got, so this is the first derivative of x. So that's what it looks like. And then I went ahead and graphed the second derivative of x. So you've got f double prime of x equals 12x squared minus 12x, and that gives us this parabola right here. So an important thing to note is that the first derivative, right, this one right here, anywhere that the first derivative is positive, so if its y value is greater than 0, then we would expect the slope to be positive on the original function. And so you'll see that that's true. So right here, the y value right at 1.5 goes from negative to positive. And so what that means is that up here on the original function, right at 1.5, the slope goes, and my minimum wasn't drawn very well. But the slope right at 1.5 goes from a negative slope to a positive slope. And so that correlates to a negative value of the first derivative to a positive value of the first derivative. And then down here it touches 0 again, but you'll see it goes from negative, touches 0, but then continues to be negative. So it never really becomes positive. And so what that means up here is, so you have a negative slope coming down, you have a 0 slope right here, and then a continuation of the negative slope. Don't confuse the fact that these are negative values with the negative slope. Here, the fact that they're below the x-axis is what's important. They are negative values. Here, you're looking at a negative slope, so it's sloping downwards. This graph, if it were shifted upwards, would still have a negative slope right here. Even if the values were positive, the slope would be negative, and that's what's important when you're looking at the first derivative. And so here, here the values are positive, values are negative. Here, slope is positive and slope is negative. So that's can be one place where it can be kind of confusing, is the difference between positive and negative values and positive and negative slope, and the correlation between those. But do pay attention to the fact that this goes from negative to positive right at 1.5, at x equals 1.5. This goes from a negative slope to a positive slope right at x equals 1.5. Now, using all of those ideas, we can continue that idea onto the second derivative, this f double prime of x. And so when we look at the second derivative, we see that the second derivative equals 0 at 0 and 1.0. And so what that tells us over here is that the slope of this graph is going to be 0 at 0 and 1.0. Because you're just doing the exact same thing, you're just carrying it one step further. So the same thing you did here to here, you're doing from here to here. So you're taking the second derivative is measuring the slope of the first derivative. And so what that's telling you is the slope is positive. The slope of the first derivative is going to be positive where the values of the second derivative are positive. And the slope of the first derivative will be negative, so you see it's decreasing, where the values of the second derivative are negative. And then, again, they become 0 at 1.0. The slope is 0 at 1.0 on the first derivative. And then the values become positive after 1.0, and the slope becomes positive after 1.0. And so what you're looking at is the idea that here you have, if you look at the values of the first derivative, here the values are a little bit negative, here they're much more negative. And so what that correlates to up here is here you have a little bit of negative slope, here you have much more negative slope. And then again, contrary-wise, here right at 1.5 and past it, you have very low values of positive, very low positive values, and increasingly positive values. And here, right at 1.5, you have a little bit of positive slope, and then as it keeps going, the slope gets more and more positive. And so then when you try and correlate the second derivative all the way back to the original function, what this is going to tell you is anywhere that the second derivative is 0, you're going to have one of those inflection points. So again, if you go back over to this image, so this inflection point correlates to a point where you have a second derivative equal to 0. So then on this side of it, your second derivative would be less than 0. On this side of it, your second derivative would be greater than 0 or positive. And this inflection point would be where the second derivative is 0. I'm beating myself a lot, but this is, I think, important to see from a lot of different angles. So again, so if you have here, this is the graph of your second derivative, where the values of this are negative, the slope is going to be negative in the first derivative, and that means the concavity of the original function will be negative. So let's see how that correlates out. So, okay, from negative infinity to 0, we have positive values on the second derivative, which means we should have a positive slope on the first derivative, which we do. So positive slope on the first derivative, positive values on the second derivative, and that should correlate to concave up on the original function. And we see that indeed we do have upward concavity from negative infinity to 0. So from negative infinity to 0, positive values, positive slope on the first derivative, concave up on the original function. So then right at x equals 0, it switches to negative values on the second derivative, which gives you a negative slope on the first derivative, which then gives you a downward concavity on the original function. So again, negative values from 0 to 1.0 means a negative slope on the first derivative from 0 to 1.0, which correlates to negative concavity from 0 to 1.0. So that means that at this point right here, 1.0, at x equals 1.0, that's where this original function switches from something being concave down to this bowl being concave upward. Right? So again, this 1.5 is the minimum of that bowl, but this 1.0 would be, in essence, the start of that bowl, because everything on this side of 1.0 is going to be concave down, everything on this side is going to be concave up. And then, so if we go back over to here, so the negative values end at 1.0, we have positive values on the second derivative for everything after 1.0, and this is a parabola, so you know that you can go off to infinity and it's always going to be positive. But so positive values for everything after 1.0 on the second derivative corresponds to positive slope after 1.0 on the first derivative, and that corresponds to positive concavity for everything after 1.0 on the original function. So again, so everything from here over is going to be concave up. Everything from here to here is going to be concave down, and everything from here over is going to be concave up. Right, and so we get those points from just looking at where the second derivative equals 0, and if it's greater than 0 or less than 0. And so then the whole idea is that you can set, once you solve for the second derivative, you can say f double prime of x is equal to 0, and then you solve for x. So once you do that, you will know where these points of inflection are, where it's going to change from one concavity to another. And so if you know what the point of inflection is, then all you have to do is you say, okay, so I know that those points of inflection are going to be at x equals 0 and x equals 1. So then your only job is to figure out, okay, well, before 0, are the values positive or negative? Between 0 and 1, are the values positive or negative? And after 0 and 1, are the values positive or negative? And so it's really easy to see that on a graph, but if you don't happen to have Wolfram Alpha readily available, if you're doing this by hand, then what you do is you just plug in. So you solve for 0, you plug in something on one side of x, something on the other side of x, you see what value you get, what your f of x value is, and that'll tell you what the inflection is over here. So So that is kind of the general idea of the whole thing. Okay, so next I wanted to go through maybe the more boring part where you're working with the actual numbers of the whole thing instead of the graphs, which are easier to see, but we'll refer back to the graphs. So the first part of the question asks us to find the points of inflection, and then it also wants us to find concave up and concave down, and then use that to sketch a rough sketch of the graph. So the first thing you're going to do is you're going to take the first derivative. You're going to say f prime of x is equal to 4x cubed minus 6x squared, right? So that's going to be the first derivative. Second derivative, f double prime of x is equal to 12x squared minus 12x. So this function tells you what the concavity is going to be like, right? So what we want to do is we want to find out where f double prime of x is going to be equal to 0. So what will you do is you just set that equal to 0. I'm going to switch colors here for a second. Let's see if this shows up. So if you say f, is that showing up? Good. If you say f double prime of x equals 0, that means 0 is equal to 12x squared minus 12x. Right away you can divide through by 12, so you get 0 equals x squared minus x. You get, if you bring this negative x to the other side, you get x equals x squared, and that can only happen at 2 points. The square of itself can only be equal to x at 0 and 1. So these are your answers right here. So x equals 0, x equals 1. Don't actually put these in brackets. That I was trying to show you that that's the answer, but don't do that. That's how you write matrices and stuff like that. So that's bad practice. I shouldn't have done that. But so your answers are x equals 0 and x equals 1. Will give you this f double prime of x equals 0. So then what you can do is you can set that on a number line, like so. That way, no. So you can say at this point x equals 1, at this point x equals 0, and then you want to try and find out what is happening to this second derivative in between 0 and 1 and on either side of that. So all you would do is you would plug in some numbers. So let's say, so we want to get something bigger than 1, so we can just say, hang on, I'm going to switch colors again. So let's say we want to test what is f double prime of 2, right? And that would be equal to, so you just plug this f double prime of 2 into this f double prime of x. So we would say that that is equal to 12 times 2 squared plus, minus 12 times 2. And so then that's going to be equal to 12 times 4 minus 12 times 2. And so that's going to be, what is that, 48? 48 minus 24, and then that's going to be 24. But the thing you really care about is that this is positive, right? You care less about what the specific value is. You care that on this side of x equals 1, any value over here on this side, anything greater than x equals 1, f double prime is going to be positive, right? So that's going to be going up. And then you can do the same thing for between x equals 0 and x equals 1. So you can say, let's do this again, f double prime, so I'll try and get my hand out of the way, f double prime of 1.5 is equal to, what is that, 12 times 1.5 squared minus 12 times 1.5, and then you can say 2 equals 1.5 squared. So then you can do, take the 12 out, 12 times 1.5 squared minus 1.5. And I don't actually know what that is, but I know 1.5 squared is going to be bigger than 1.5, so I know that's going to be 12 times some negative number. So it's negative something something something. So I know that there's going to be 12 times some negative number. So I know that in here it's going to be negative. So I know that this is going to be a negative value. This is a positive value. And then you can do the same thing over here for x less than 0. You can say, f double prime of, let's do -1, is going to be equal to 12 times -1 squared minus 12 times -1. And so then that's going to be 12 times -1 squared is just times 1 minus 12 times 1 times -1. So you're going to have 12 minus -12, and so that's going to be again plus 24. But the big thing is you care about that it's positive. The value, or the specific number, doesn't really matter that much. You care that it is positive on this side. Okay, so then next thing you want to do is you want to take all that information. So right now we just solved for what's going to happen. So we figured out where f double prime is going to be 0, and then we figured out if it's going to be positive or negative on either side of those zeros. And so again, if we go back here, what we just solved for was we found where the values of f double prime are going to be less than 0, where the values are going to be 0, and where they're going to be greater than 0. Okay, so that was all of this right here. And they match up. So we've got x equals 0, x equals 1. This is where f double prime is 0. This is where it's positive, negative, positive. And that totally correlates to this graph. So you've got positive values, negative values, positive values. So then that is going to go back and correlate to where this slope is positive, where this slope is negative, where this slope is negative. Where this slope is positive, and again, that's going to correlate to concave up right here, concave down right here, and concave up right here. So this graph, where you have positive values in the second derivative, if you have positive values in the second derivative, that's going to give you concave up in the original function, concave down in the original function, concave up in the original function. So values, concavity, here we've got values to slope. Okay, so that's the correlation between all the first derivative, second derivative, and stuff like that. So then, yeah, actually I'm going to go ahead and stop the video there and then make a different video for the next portion. Good luck. Ask me any questions you have.